So, hello everyone. Thanks for having me here. My name is Stefan. Until recently, I was a postdoc here in the quantum optics group, and a few months ago, I started my own group at the University of Massachusetts Amherst. I'm also part of the Center for Quantum Networks, which is one of the NSF engineering research centers. It spans a number of universities, and I have some of the modeling responsibilities in this center. So some of the goals in the center, to describe them, let's just briefly look through what typically we describe as the quantum technology stack. So we start from designing materials that have the necessary quantum properties, and there are many experimentalists in the center that are actually focusing on that work. Many of them also do analog control necessary to turn these into something that starts resembling probably noisy digital circuits, and there are other researchers, mostly theorists, that work on error correction and quantum networking and quantum algorithms in the center. And a lot of the goals we have, a lot of the difficulties we have to do with when someone working very high at the stack, a network scientist that might know a ton about routing and so on, needs to inform their work based on experimental work, based on what's truly available in the hardware, based on what's actually the best possible entanglement generation scheme that is developed by other researchers in the center. Or in the other direction, someone who's optimizing their analog hardware, their transduction, the quantum transduction hardware. They want to know what are the most pertinent parameters they need to optimize. And they frequently have difficulty getting informed answer based on the needs of the higher levels of the stack. So what we're trying to build is tools that help a little bit more with that type of full stack design. The things we need is some form of relatively easy symbolic way to describe various algorithms that are happening. We don't want to have everyone in the team need to learn every single state-of-the-art simulator. Some things can be simulated well with a Clifford simulator, some things can be simulated well with a state vector simulator, and there were many other techniques discussed today that are helpful. But we want the network scientist to just say, here is my entangled state. You figure out how to simulate well the protocol I'm working with. We also want declarative noise models so that, again, someone working higher up the stack doesn't need to learn how to use Krauss operators or how to implement Monte Carlo of polychannels over a Clifford simulator. And then, if we have these tools, for it to actually work, we need to have them translate all of this to the backend simulators. Some of those backend simulators are things that you guys described today. Some are simulators that we built because we didn't really find anything else in the ecosystem, whether Julia or Python or anything else that was good enough for our goals. And because we have a lot of networking to do, we also need a discrete event scheduler. Thankfully, those are somewhat easy to just bolt on top of this, but if we're going to build a holistic system, we can also try to provide some nice tools for that. For instance, NetSquid is its main value proposition is this discrete event scheduler, but the simulation inside of it, if you want to, you can mix NetSquid and Qiskit, for instance. And for this to end up being useful, hopefully it would be sufficiently Lego-like for the users. OK, so let's focus on a couple of those tools. First, I'll go high level in terms of the symbolics that we're working with and so on. And then, if I have time, I'll discuss some of the backend simulators we have developed that, that actually do the heavy lifting. So say you want to describe some state that's being generated in your network, but you don't want to pick a simulator. You want to be agnostic from that when you're setting up your initial study. We have tried to build a fairly simplistic symbolic algebra system for that purpose. There are other efforts in the ecosystem to do that, and we have slightly different requirements, but we're keeping close look on other options, and we're definitely very focused on being interoperable with other tools. But what we have developed as an embryonic attempt in that direction is a simple symbolic algebra system. Say you define your Z1 state, an eigenstate of the Z poly operator, or some tensor products and sums and so on of such states. And that provides you with some symbolic representation. Importantly, we don't want to limit ourselves to just qubits. We have a lot of analog physics that we worry about while we're developing this hardware. We are not people developing just circuits and algorithms. We want to model transduction. We want to model continuous variables entanglement. So we're not limiting ourselves in this setup to just circuit simulation. The symbolics would work for other types of quantum states as well. But the value we derive from that symbolics is that we can then easily translate the symbolic expressions to backend simulators. For instance, the Express API, by default, will translate this expression to something in the quantum optics package. And the behind-the-scenes simulations, if we're doing state vector simulations, will be done by quantum optics. Again, because we don't want to limit ourselves to qubits, and that's one of the better toolkits that we currently have that does any quantum analog dynamics. Or if you want to do a large-scale error correction over thousands or tens of thousands of qubits, we probably would want to have noisy Clifford simulator. So the symbolic expression behind the scenes can be translated into a tableau that can then be used by a Clifford circuit simulator that would be much more efficient, but just for Clifford circuits. And that Express interface I mentioned, it is the main piece of development that we actually need to invest time into. It has two steps, basically the Express, where you give it a symbolic expression, the type of backend representation you care about that the simulator interface might decide on its own, and the use case, because in some cases representing something as a state versus an operational state might require different operations on the back end. And then there is the Express no lookup, which is the underlying implementation. And we are separating it that way because we're actually performing some form of caching. We don't want every single time we are transforming a symbolic expression into a numerical object to have to do that from scratch. Some of those operations might be expensive tensor products. So the Express operation, by default, will cache the object that was being translated. So if we start with the X operation that we want to translate to some backend, by default, Express will translate it to the quantum optics backend, and the metadata for that symbolic object will contain a cached representation. And if we then use Express to prepare a Clifford representation, again, the backend, the metadata content of the symbolic object will contain that representation as well. So future uses of that, as we're building bigger syntax trees, don't need to worry about repeated computation. But anyway, the goal here is for this Express API to be used by the actual front-end tool that the scientists will be using. So again, imagine a network scientist that has a vague understanding of entanglement protocols, but what they actually care about is routing scheduling. They don't want to learn quantum optics or quantum Clifford or any other tool for that backend. They just want to simulate their circuit. So what they can create, for instance, is this register of 3 qubits, and we have a bunch of Mackie recipes because we like to make debugging a little bit easier. So that Mackie recipe for this register object just gives you a pictorial representation of something with 3 slots that can contain some states. And then we use the symbolic X1 object, and we will be initializing the first slot of the register we just created. Here I'm plotting a register with 2 slots, not with 3 slots. And I'll just run through a couple of examples of this API. For instance, again, here we have some symbolic object Z1 that will be put as an initial state for the second slot of the register. I'll perform some CNOT gate, and I don't know whether it's visible on the screen, but now that these two slots that used to be two completely separate state vectors, now that the CNOT operation is performed on them, the simulator automatically decides to represent them as one larger state vector over a larger Hilbert space. And to mark the fact that they're in one single Hilbert space now, there is this slight line joining the black diamonds. So rectangle means slot, diamond means some state stored in that slot, and line means that these states belong to one big system, and they're just subsystems of that big system. We are lazy in terms of building up the large system because that can let us represent, as long as we know that we don't need to track entanglement, it can let us represent a very large number of qubits, even in a state vector formalism. And what actually is being stored in that slot, again, depends on the decision made by the user or by the front end of the simulator about which representation to be used. So it can start with a Clifford representation that's very efficient, and only when it notices that you're applying a non-Clifford gate, it will be translating to a state vector formalism or some other formalism. We're still early development, so we don't have many backend tools available yet, but I'll discuss this shortly. So what's actually happening is that we have this API of, say, the apply function, where we'll be applying some operation to some registers at a certain time. We're also tracking time because that might be important for some background noise processes that are happening. Well, the apply then figures out from these registers what are the actual states and what are the subsystems within those states that need to be manipulated. And if the operation is symbolic, it expresses it into the necessary backend simulator, and finally dispatches on some low-level simulator that for the moment is mainly quantumoptics.jo and quantumclifford.jo. And we have a couple of other convenience methods like projective measurement and observables, and there's certainly need to expand more in terms of capabilities here, but we're taking it slow just to ensure that everything works with the current backends. And some things that we're trying to develop is, as I mentioned, tracking those background noise processes as well. Because, again, in quantum optics right now, if you want to track a noise process, you need to write down the Krauss operators, for instance, or the Lindblad dynamics generators. You need to embed it in a larger Hilbert space because probably you have multiple systems, a qubit here, a harmonic oscillator here. All of this needs to happen manually. We want to automate a lot of this so that it's easier to use for people that are not quantum mechanics theorists. And one of the tools we're building in that direction, for instance, is one of the APIs we're trying to build out is basically defining background properties for the various slots. Again, not qubits. Some of those can be harmonic oscillators, some of those can be other quantum systems. So for instance, here pictorially, say we have a register with 3 slots. The first one is experiencing a T1 decay. The second one is experiencing a coherent error, some over-rotation. The third one is experiencing some non-Markovian bat. And you want to implement this circuit on them where U1 is applied on the first 2 subsystems at some time. U2 is applied on the second 2 subsystems. And those are at different times. So the simulator, if we're applying say, the CNOT gate at time tau 1, the simulator on its own decides that the proper way to model the T1 decay would be with a Krauss map. The proper way to model the coherent error would be by actually evaluating Schrödinger's equation. But then when we have this entangled system after the entangling gate has happened, we cannot model the error separately here, so we need to actually model some larger Lindblad equation to take into account both of those noise processes on those 2 subsystems. Some of those are not actually implemented. We definitely don't have much support for Nakajima-Zvanzik equations for non-Markovian bats, but they're on the to-do list. The value proposition here being, again, that for a network simulation, for something where it's really important to keep track of time as things are happening, as you're waiting on other nodes, we really want to make it easy for someone to track these things. And as I mentioned, in that context, we also need a discrete event scheduler. Currently, we're somewhat invested in what used to be called SimJulia. But there are other options to consider. The Julia ecosystem is not well developed in this area, I would say. But on the other hand, the Python ecosystem also is somewhat lacking in terms of discrete event schedulers. So as an example of what the result of a user doing something with this tool is, especially focusing on some of the visualization and debugging tools we're trying to build in, this is a chain of 5 repeaters on which there are 3 concurrent processes happening. Between each neighbor of repeaters, there is entanglement being generated. And then on each repeater, there is concurrently swaps happening in order to make the entanglement longer range. And then also on every pair of repeaters, entanglement distillation processes are happening, trying to make the entanglement higher quality. And this animation here is, again, a couple of Mackie recipes, fairly automated. And this plot here, similarly, just a couple of lines of Mackie and some instrumentation we have built into the tools we're setting up. It's still, I would say, that part of the setup is not as user-friendly as we hope, but we are very early in the development stage as well. And actually, it's really wonderful how easy it is to make web apps with Mackie. So this is an actual example that's running on a server at my university. Hopefully, the connection won't crash. What I'm showing here is a full simulation on setting up a 6-qubit cluster state between NV center nodes. Each register here is 2 qubits, 1 electronic qubit and 1 nuclear qubit. They're in this grid formation, and we'll be establishing entanglement between electron qubits. We'll be tracking real-time the networking communication necessary to synchronize that happening. We'll be transferring that entanglement into the nuclear qubits. And the goal is to establish a large-scale entanglement. Pictorially, we'll be representing the quality of the entanglement links. And again, in terms of instrumentation and Mackie recipes, all of the logs and channels and other synchronization primitives that the networking scientist cares about are also fairly automatically plotted. It's 2 or 3 lines of code to make this plot after you've set up your logs and so on. And hopefully the connection works, but yeah, that's pretty much it, what's happening. You saw very brief flash of the various logs being triggered and untriggered on this side, the tracking of what links were established here, and various instrumentation about quality of entanglement. And you can see how the entanglement, after it's finally established, it goes back down because of the background noise processes.
Can you run that again? I wasn't ready for it.
Let me try. It seems to be loading. I'll try to scroll back to it. Yeah. Oh, it's here. Yeah, so maybe I should have put a sleep command inside of the event loop. But yeah, 3, 2, 1. Yeah, definitely a sleep statement for the next time I'm giving that demo. Yeah, this is literally a web app currently available on the internet that was made with not too many lines of code, thanks to using the tools we've been developing. Of note, actually, I'll skip some of the other demos I have. The alpha version of this software is available online. I'm very interested in complaints, issues, experimentation. I plan to be at the hackathon here so that we can discuss how I can exploit your work to make my work easier and add some backends. And in terms of backends, I just want to mention a couple of the simulators we've developed for this. First, we were really, actually, first a call out to the rest of the Julia ecosystem. I'm most familiar with quantum optics, again, because I'm doing a lot of your typical analog physics, but it's really, there are a lot of other tools that can easily be incorporated here as well. In terms of what we developed ourselves, mainly that's the quantum Clifford package, which is probably the most feature-rich package for quantum Clifford algebras in any language. There is STIM, which is wonderful when you're doing circuit simulation, but it's lacking in some other features. So in terms of that package, as I mentioned, it's an algebra tool, not just a circuit simulation tool. So you can do a lot of interesting things with stabilizer states, partial traces over them, projections and initializations, enumeration of possible gates, generating random states. And it's also a circuit simulator. In that context, STIM is probably a better circuit simulator if you just want fast Monte Carlo. But we have something that, again, no other package has. We actually do symbolic perturbative expansions over what the circuit will be doing. If you have some noise parameter, like here, this is a purification circuit, and you have some noise happening at the beginning, and you want to deduce what's symbolically the probability of success for your purification circuit, the package is capable of that. That's a whole other topic that we can discuss later. And we have a package specifically for simulating entanglement distillation, which is orders of magnitude faster than any other option. We have now a couple of students working on extensions to the quantum optics.geo infrastructure. And something I want to really thank the quantum optics folks is that they really helped as we were setting up this quantum interface package that lets us have a consistent naming conventions and function names and one single namespace for a lot of the infrastructure, like a projective measurement, gate application. It made my life building those back-end infrastructure much easier thanks to these folks being so open to committing to one single interface. I would be very interested to discuss this during the Birds of a Feather session. It was extremely useful for me to have this resource. And with that, we're hiring, and I'm open to questions.
Okay, so we have a few minutes for questions. If anybody has any, just raise your hand and I'll hand you the mic.
I could ask something quickly. So in the, first of all, it's a nice talk, and a lot of nice stuff is kind of overwhelming the quantity. But I know you were very concerned with efficiency with quantum Cliffords and did a lot to make that work. And I wonder, the symbolic thing, if I understand correctly, you were using the symbolic package or the utils at least.
For the very beginning of the talk, when I was talking about overall things, that was the symbolics.geo, and we built on top of it.
On top of it.
The circuit symbolics, any Julia or Python symbolics package can be used with it. It's as long as you have something that can represent the number interface, whether symbolically or not, Nemo, symbolics, Taylor diff, Taylor series, sympy.gl, all of those would work fine.
Okay. And the thing with the metadata, though, that where you were updating?
That was, so my last statement was about the Clifford circuit simulator and perturbations on it. What the first talk of symbolics, that's the one that's dependent on symbolics.gl. That metadata caching is with symbolics.gl.
Yeah, I'm wondering, so it seems like you're not, I don't know what the performance of that would be. It seems like for large systems.
Yeah, that's not something I'm trying to optimize for. Yeah, so the performance probably will be very similar to sympy. So there will be a lot of runtime dispatch. It won't have, and I think Roger is working on something that's much higher performance by using something in the family of unitypers, some types, Expronicon. There are a lot of tools for very high performance symbolics. I don't need that type of symbolics for my work, but I would definitely exploit it when that gets developed.
Is this for researchers or pedagogical, or who's your target?
Currently, mostly researchers. I'm using it a lot for pedagogy, but the people that won't use it are truly network scientists that don't want to use quantum optics.jl because they don't want to learn about Hamiltonians. And in the other direction, experimentalists that don't want to make their own network simulations to learn what parameters to optimize in the hardware.
Cool. So with that, we are right at time. So thanks again to Stefan for his great talk.